Hi again. The example that we did can be very easily shown by the simple homemade setup that you can have at home and experiment that you can try at home. Here is a nice picture from Doug Edgerton in 1934 picture. Doug Edgerton was a pioneer of high-speed and flash photography who worked extensively in MIT. And he did this nice photo that a tap of water lets the jet impinge on a upturned can, and as you can see, there is a disk of water that is expanding on this can, and finally some of the rim gets out and then breaks into smaller droplets that fall down vertically due to the action of gravity. Now, if this can was smaller in area, you could have seen actually the expanding rim in a better way. And indeed, Edgerton was not the first person who thought about this experiment. Before Edgerton, a very famous French physicist and scientist, Félix Savart, he did many measurements and experiments on jets, impinging jets, where the jet was either impinging on a single target or where two jets were actually impinging head on or face on in a 90-degree angle collision to each other. And he looked at what would be the geometries that come out of these experiments. He was way ahead of his time. He did these experiments many centuries ago, and he actually did without use of any high-speed camera or photography actually in that time, just by observing things with eye and making drawings of his experiments. These are drawings from his own papers. He could actually report certain interesting aspects of this phenomenon. There are many recent studies on this phenomena, and here there are some nice images that show this phenomena happening. You can see, for example, on the very top, this is the impinging jet that is impacting on a circular disk. And then as a result, a very thin liquid sheet expands radially outward, and at the very rim of the liquid sheet, you can see that it's starting to break up into single individual droplets that are falling vertically downward. You can clearly see that if you change the dimension or the speed of this jet, the sheet that looks here relatively flat and stable can become unstable, and waves can be generated. The very low, the lowest image shows the generation of unstable waves that are radially expanding. And that's a limit that we didn't really study in this example that we did in this recitation or overall review. That's a slightly more complex phenomena that requires also taking into account the interaction between expanding sheet of water and ambient air around in terms of the shear layers and the shear instabilities such as Kelvin-Helmholtz instability. We didn't really talk about this in this course, so we are not going to talk about that in this video. You can also try viscous fluids, and you can see even for a viscous fluid, again, the same scenario repeats itself, an expansion of the sheet, and finally at the rim where viscous droplets separate from the sheet in terms of elongated downward ligaments, which finally break into individual droplets. What we really tried to model for the case of a stable liquid sheet is this simple model that is a jet impacts and it forms a very thin sheet that finally at a radial distance r equal to r breaks into single individual droplets. We showed that it's relatively simple to solve this problem if you take the right contour volume and just write a simple balance of forces and balance the entire radial force with the incoming radial momentum, and that would give you a nice relationship that the radius of the jet normalized over the initial diameter or radius of the impinging jet should be proportional linearly with the Weber number. Here are the measurements, and you can see that the initial measurements up to a certain critical Weber number, which is order 1000, all show a nice slope of 1 on a log-log scale, which is the prediction that we got from our simple two-line of modeling and analytical expression that we had, this line that is there. The reason that you have a second region which is shaded with red, that you have a different behavior there, is what I mentioned before, is the presence of unstable waves. As you go to large enough inertia, this liquid sheet is not anymore stable. This liquid sheet, rather than remaining flat, it starts flapping into the air, and these wave-like structures appear in this liquid sheet that move radially outward, and that would give us a totally different balance of momentum. And we should definitely think about interaction between air and liquid in terms of shear layers, and the so-called Kelvin-Helmholtz instability becomes extremely important for that. So that's why our result is valid until we have a smooth liquid sheets. If we go to flapping or unstable liquid sheets, we have a different scaling that we can't really talk about it, but that's also an interesting subject. So you can see that despite the amount of so many different topics that we covered in this course up to module 3, and despite the fact that they can help you to understand many interesting phenomena in a nice way, there's still quite a bit unknown parameters and phenomena happening in this field that require maybe even further knowledge and further studies in fluid mechanics. So by no means this is not the end of fluid mechanics. You should be all excited to take more courses and learn more about different aspects of fluid mechanics. One important aspect, for example, is to understand this part is the concept of hydrodynamic instabilities. Things such as very fast moving sheets of water next to air can cause or can lead to so-called shear instabilities, which are called Kelvin-Helmholtz and are a subgroup of hydrodynamic instabilities. We didn't really talk about them that much, and if you are interested, there are courses that are available on OpenCourseWare of MIT that may actually talk about this in more detail. The other aspect of this phenomena that I want to just talk about it a little bit comes from actually a familiar face to you. You remember Gustav Magnus, the person who actually did the experiments on Magnus effect initially. He also did a nice study where he had two colliding jets. So instead of a jet colliding on a target, he actually made two colliding jets to impinge to each other with a certain angle. So you can easily see that now you don't have the circular symmetry anymore, because the impinging jet has a certain angle. So you will send more momentum probably in this direction to the right, and less momentum to the left. And this will lead to a kind of lack of or breakage of symmetry. The shape is not anymore a circle. It looks like a bay leaf or a certain interesting structure. Again, in the times that high-speed photography or even photography were not available, he just observed these nice experiments by naked eye, and he made very precise drawings, which are amazingly nice and accurate. You can clearly see he has noticed that at the very rim of this sheet of liquid, which has a shape similar to a bay leaf, there are certain small droplets that are getting separated and breaking into the air. And indeed, this is exactly what happens if you repeat this phenomena in 2017 or 2018. These are the images we did in the lab. And this was actually part of the work I did in my own studies during postdoctoral research. And you can see if you have jets colliding to each other with a certain angle, you can use the concept of high-speed photography with what we call air-filled flashes. It is air-filled or air-gap flashes. They release really high voltages up to 20,000 volts in a fraction of a microsecond, almost 300 nanosecond. So you can freeze time in a very nice manner. And if you freeze time, you can clearly get a nice picture of this thin liquid sheet that indeed has the shape of a bay leaf. And sometimes people call this fish bones, because it may look like a fish bone because of the structures that is formed at the very end or tail of the structure looks like a fish bone. And you can clearly see that in a repeatable manner, the rim of this liquid sheet is becoming unstable, and droplets are getting separated from this liquid sheet, and they fall down due to gravity. Here, clearly, you can see that we don't have the axisymmetric circular case anymore because of the breakage of the symmetry due to the angle. But again, if you consider a balance of momentum and find out how much more momentum you have downward, you expect that the sheet should expand downward in a larger distance than upward. And that's what exactly you see. So again, even for complex problems like this, you clearly can use some of the concepts you have learned in this course in modules 1, 2, 3 and apply them to these problems. The very nice optical illusion that you can play with is you can put a background picture a little bit away in the back of this phenomenon. And since you are generating single individual droplets and sometimes elongated cylindrical filaments, and these are all made of water, you actually are generating some water lenses. So a spherical droplet acts like a water lens, an elongated cylindrical filament acts like a cylindrical lens, and then you can see a zoomed version or reflection of the background image, which here was a falling pumpkin, because this was an entry that we sent to a conference for American Physical Society Division of Fluid Dynamics in Atlanta in Georgia, and the symbol of that conference was a falling pumpkin. So you can clearly play with this. You can, if you like, you can put the map of the world. Some people have done it, and inside these droplets you can see a very nice spherical reflection of the map of the world. Last thing that I want to finish this overall review of slides is the concept that, as I said, these were all Newtonian fluids so far. We talked about Newtonian fluid mechanics extensively in these 3 modules that we provided for you. But there is a completely different branch of fluid dynamics which deals with non-Newtonian fluids. So if you add a little bit of polymer, for example, such as polyethylene oxide, and very little means 1 part per million, a very small percentage, weight percentage. These very long chain flexible polymers, they may not show that much difference initially. You may think the liquid looks very much like water, but if you go to fast enough processes, such as, for example, this experiment that we did with impinging jets, you can clearly see that the elongation of these polymer chains will lead to some counterintuitive results, especially when you look at the break up and pinch off of elongated filaments and stretched capillary bridges. These effect of viscoelasticity that comes from the extension, fast extension or elongation of polymer chains in the phenomena or the fluid phenomena that we are studying, is a very nice and interesting branch of fluid mechanics that we call non-Newtonian fluid dynamics. That's also a part of fluid dynamics we really didn't have any time to cover in these 3 modules. I encourage you, if you are interested, to check open courseware softwares or websites such as MIT OCW, and there are really interesting notes and topics offered there that you can learn more about this subject. With this, I thank you all for being with us in this relatively interesting journey in fluid dynamics. And I hope what we have provided for you within these 3 modules will be helpful for your overall knowledge or research or general concepts that you can use in life. Thank you, and best of luck in everything.